Good morning. I want to tell you a little bit about some work that our team has been doing for the last few months, not so much about the science that you would do on the lunar surface and later on the Martian surface, but about how we might better enable that science, your science, through proper human-machine teaming, and in particular, autonomous human and machine teaming. So proposing, at least for the sake of argument, but there are some good operational reasons, proposing that when you get there, the humans and the machines will form a tight, cohesive team, humans and robotic assistants, and you would want to enable them to work independently from other teams, independently from mission control, for a variety of reasons. So let me put it into a little bit of context with just a story. Jack and Jill put on their spacesuits and go out and do an EVA on the lunar surface. Again, later on, what I'm talking about here is certainly applicable to Mars, even more applicable because of the autonomy considerations, which will be extreme on the Martian surface. So what we're proposing here in terms of lunar exploration is using the moon as a test bed for Mars, at least in this particular aspect of things. So Jack and Jill put on their suits, they go out and they do an EVA, but they do EVAs day after day after day for hours at a time. Could go on for weeks at a time, in the later stages maybe of the Artemis program for a month or more. So they're going to start getting worn out. They're going to start making mistakes. They're going to start getting tired. They're going to show physiological and cognitive deconditioning. The same thing with their robotic machine assistants. There'll be degradation in the sensors. There will be other problems. So what we're proposing is that in order to maximize science return and just everything that people are doing, people and machines are doing on the surface, not just science, but also operations, excuse me, setting up habitats and things like that. To optimize those things, you want to track in real time the capabilities of the humans, the capabilities of the machines, the robotic assistants, and make real-time interventions accordingly. So if Jack starts making mistakes, starts throwing the wrong switches, is making inaccurate reports back to headquarters would presumably be in the habitat, then we start to track that. If Jill is showing signs of impending fatigue or dehydration, which we can get from a variety of biomedical sensors that we can put into the suits, maybe voice stress analysis, those types of things, track that, put that into a model. The model is where the magic happens. That's the black box. We do not have that model, by the way. That's what our research project is partly about. But you do the same thing for the machines. The machines have built-in sensors. You can see if the machines are starting to be degraded as well in their performance and their capabilities, and then make interventions accordingly. Now, what are interventions? In the case of humans, it could be as easy as taking a break. You're about to hit a wall. When you hit that wall, we know that you are a high-performing individual, you're resistant to asking for help, but we need to step in now and tell you to step back, take a break, have some Gatorade, take a rest, whatever it is, because you're about to jeopardize not only yourself, but the rest of the mission, including your teammates and colleagues out there. Same thing for the machines. If the machines are showing degraded capability, maybe you give some of their tasks, their nominal tasks, to the humans, and vice versa. And rescheduling, if there's going to be a myriad of tasks that have to be carried out on the planetary surface, some of these tasks are interdependent with each other. If next week the crew has to go out and start building a habitat, then this week's set of EVAs may have to lay the groundwork for that by putting some infrastructure in place, while at the same time also doing some science. Some of those are more important on a time-critical schedule than others. So if there are things that absolutely have to be done in order to get ahead of schedule, stay on schedule, next week you want to prioritize those and start offloading things, start shedding tasks that are of secondary priority. And You want a computer algorithm to be helping with that because the same degradation in capabilities, especially on the human side, that may lead to the need for that rescheduling are the same things that are going to make it very difficult to do proper rescheduling, especially in real time. So I think that sets the stage for what we're talking about here. We're still in the early stages of this, by the way. This is an interdisciplinary team we have at Johns Hopkins. I'm at the School of Medicine. You have people from the School of Engineering, people from the Applied Physics Lab, including Carl Hibbets, who's here in the back. If you have ideas about what I'm saying here today, please feel free to approach us and give us ideas, your ideas about how this might be applicable to your particular science and what you'd like to see accomplished on the moon and later on Mars. So this is some kind of a summary of what I've been saying. Our goal is to maximize productivity and resilience so that when things start to go wrong, the mission can still move ahead and accomplish goals. Productivity and resilience of autonomous Moon, Mars, crews, teams, human-machine teams. Down at the bottom, you see further the context of what this is involved in. Multiple EVAs over weeks or months. Unexpected and anomalous situations. I can't tell you what they are because they're unexpected. But if we didn't expect the unexpected, there'd be no reason to send humans in the first place. So we know that things are going to go wrong. We know that there will be targets of opportunity that were not planned for in terms of exploration. We know that things will break that were not accounted for. Autonomy for mission control, a number of reasons. First of all, in later stages, it might be that there are multiple human-machine teams on the surface working independently. So you want to grant them the autonomy to make their own decisions. Another thing is that astronauts really like autonomy. They like to be independent. They don't really like mission control looking over their shoulders all the time until something goes wrong. But also, decisions need to be made in some cases very quickly based on, again, targets of opportunity, exploration, things that are found that were unexpected. So you want to grant the human-machine team autonomy as much as possible while there are changes going on in the human and machine capabilities. I've talked about some of them simply degradation over time, over repeated EVAs, and the idea of multiple interdependent tasks which would lead to rescheduling. These are just a few of the things that could be issues and some of the things that we would want to have measured. Let's start on the left-hand side. In the human, there are sensors for many of these things: dehydration, biochemical status, electrolytes, things like that, voice stress analysis. I left a gap there because on the bottom, the last three bullet points are something that we call, it's called in the community, embedded measures. These are things that we think are important to measure. There aren't really any good sensors for these things in a real-time setting, but maybe there are other things that you can measure that the crew is doing anyway that give you the required information. So things like, you would really want to measure cognitive function. To measure cognitive function in the laboratory, you have to stop what you're doing, sit down 20 minutes, 30 minutes or more, take standardized tests. That's not going to happen during an EVA, not even close. But maybe you can track performance errors. Maybe you can track the amount of time it takes someone to respond to a question or a command. You can track sluggishness, lethargy. You can track all of those kinds of things with the proper sensors and then put them into an algorithm and extract that kind of information. And then what do you do with that information? Well, this is just one example of an algorithm that we might be able to use. So gentleman Martin Scheffer has written a number of papers on this idea of early warning signals for critical transitions before people hit the wall or their machine counterparts or the team interacting. Are there signals in the time series of these various sensors and measurements that will tell you something bad is about to happen? In some cases, the answer is yes. So you could feed that data on a regular basis into that algorithm, and then the algorithm sets up a red flag that then just does not dictate, but advises the crew, maybe it's time to do something. And by the way, the algorithm can make some suggestions. And these are some of the suggestions. I've already talked about some of these things, including task offloading, but also what we might call reverse mitigations. If the crew and the machines, the team, is working at better than anticipated capacity, maybe you want to start loading them up with more. So you pull things out of your back pocket that you had saved for that kind of circumstance, get ahead of the schedule. Again, with a rescheduling algorithm that would help do that. So again, what we're talking about here is the proper integration of humans and machines for autonomous teaming, starting on a lunar surface to increase the productivity of science, and then later, hopefully, being applied on the Martian surface where autonomy will be extreme. Thank you.